Hi guys, this is Algebra lesson 7-5. It is called, here, let's write this down because you're writing it in your notes. Lesson 7-5, and it is called Exponential Functions. Up until now, our functions have all looked like this: y equals mx plus b, and we've just had x, simple x, not x squared or x to the third or anything, and these all make lines, straight lines. But now we're going to have something that looks like this: y equals a b to the x, and now x is the exponent. These are really interesting situations, especially if we're dealing with money or bacteria or radioactive material or things like that, and we'll talk about that as we go along. But these do not make lines. They make very interesting equations. Let me show you a little more about this. By the way, this is our key concept 1. And what you need to know about this is A is going to be a starting amount. B is going to be a growth factor, or actually a decay factor. I don't know if we usually call it that, but it might be growth or it might be decay. And then x and y are variables just like normal. So we might see something like this: y equals 2 times 3 to the x. 2 is going to be my starting amount, whatever this is I'm talking about. 3 is my growth factor. That'd be a big growth factor, multiples of 3. And x and y are going to be my variables. Then here's another one: y equals 4 to the x. And here what we're seeing is 4 is our growth factor. Our starting amount is going to be a 1 because there's really nothing in that equation in front of the 4, right? Here's an interesting one. If I see y equals 1/2 to the x, then this is my growth factor. It's not really a growth factor. Anytime I have a fraction, it's going to be a decay factor. So anytime I have a whole number here, it's going to cause growth, and anytime I have a fraction, it's going to cause decay. In the case of this problem, our starting amount is still going to be a 1. But our growth factor, that's going to be the number that has the x on it as an exponent. The growth factor or decay factor is going to have the x on it as an exponent. All right, so let's have a look at this. This problem says graph y equals 3 to the x. So if I made a little table of values for x and for y, I might plug in some numbers like -2, -1, 0, 1, 2. Actually, let's go ahead and let's plug in a 1/2 for fun, and then a 1 and a 2. So if I plug in a -2, I get y equals 3 to the -2. What does that mean? Remember that a negative exponent just means put me in the bottom of a fraction. So this is 1/3 squared, which is 1/9. And then let's look at y equals -3 to the negative, whoops, I don't know why I said negative 3. That was strange. Y equals 3 to the negative 1 is just y equals 1 over 3 to the 1. So that's just 1/3. Y equals 3 to the 0. 3 to the 0 is just 1. Anything to the 0 power is 1. Y equals 3 to the 1/2. Remember, that's going to be a square root. The square root of 3 is actually not a very nice number. It's approximately 1.73, but the number goes on forever like that. Y equals 3 to the 1 is just 3, and y equals 3 squared is 9. And so if we were to try to graph this, I'm going to go ahead and take off all of my scratchings here so you can see the graph. And we don't really need much in the way of the negative part of this graph. This is x, this is y. And our first point is negative 2 and 1/9. So here's negative 2, and 1/9 is barely anywhere right there. The next one is negative 1 and 1/3. So that's just barely squeaking up just a little bit. And then 0 and 1. And then 1/2 and 1.73. What's it like here? And then 1 and 1, 2, 3. And then 2 and 1, 2, 3, 4, 5, 6, 7, 8, 9. And just for fun, look what happens when we put the 3. Y equals 3 to the 3rd power is 27. So that's going to be like way, way, way up there. So if I were to actually connect these like this, it looks like this. I'm going to do a very smooth job of connecting that. But exponential graphs look like this. So this is going to keep getting smaller and smaller and smaller and smaller and smaller and smaller. And it's hard to draw, but it never actually touches the x line. It's just going to hover above it. That is called an asymptote. That's free today. And then it climbs, and really we get here, and then it just starts to build and build and build and just goes exponentially crazy. So this growth factor was pretty large, a growth factor of 3. And our starting amount, remember, was 1. So this is our A and this is our B. A is our starting amount, which was here, and our growth factor is 3. So it is going to increase by a multiple of 3 every time we move over. 1, 2, 3, 4 would be 81, and then I don't have the rest of those memorized. Just notice how incredibly large it's getting as it goes up there. This is exponential growth. Means we are tripling every time we move over 1. We are tripling what we already have. It's phenomenal growth. So if you are an investor, this is the kind of growth you want to see. All right, but what if we have a situation like this instead? Y equals 1/3 to the x. So notice that when we don't have a number right here, this is a 1. That'll be our starting amount, and our growth factor is actually 1/3. So let's watch what happens when we have a growth factor of 1/3. Let's make a little chart here. X and Y, and probably don't need quite so much room in my chart. Let's just put a -2, and then maybe a 0, and then let's just do like a 2. So if I did this, I'd have Y equals 1/3 to the -2. Remember that the negative in the exponent is going to flip our fraction over. So we're actually going to have 3 over 1 squared, or y equals 9. Y equals 1/3 to the 0 power. Anything to the 0 power is 1. And then y equals 1/3 to the 2nd power is going to be y equals 1 squared is 1 and 3 squared is 9. So that's just 1/9. And then if we kept going, notice that it gets smaller and smaller and smaller. If I were to put a 3 here, this would be 1 over 3 to the 3rd power, which is 1/27. That's really tiny. If I put a 4 here, it'd be 1 over 81. Itty bitty fraction. If I go the other direction, I'm going to get bigger if I'm going backwards in the negative direction. Okay, let me show you what this looks like if we graph it. Here's your x, here's your y, and back here we have -2 and +9. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I went back to -3, I would be way up here on 27, and then -4 would put me way up there on 81. So this is coming from way up high. 0 and 1 is a point here, and then 2 and 1/9, and then it just gets really small fractions. So what's happening is this is coming down like this, and then it just hovers, and it gets smaller and smaller and smaller, and it's very hard to draw because it just gets smaller and smaller. But because we're always cutting something in half, we never get to nothing. And this is called exponential decay. So we are coming down by this, quote, growth factor. It's actually not growing at all. It's decaying 1/3. It's decreasing by 1/3 every time. So we start big and come down, and we get very, very, very small. So exponential growth is always going to look something like this. Exponential decay is always going to look like something like this. All right, so we can identify exponential behavior from like a table of values. Let's say we have these numbers. We have 0 and 64, 5 and 32, 10 and 16, 15 and 8, 20 and 4, and 25 and 2. And what will happen is we are looking for the pattern where we are multiplying by something. And so what I usually do to figure this out is I kind of go backwards, and I will put the 2 over the 4, and that's 1/2. I will put the 4 over the 8, that is also 1/2. I will put the 8 over the 16, that is also 1/2. I will put the 16 over the 32, that is 1/2, and the 32 over 64, which is also 1/2. So this is actually my growth factor. If I went back to 0, as we go up, it is growing, and it's growing by a factor of 1/2. So this is exponential, and I can identify it that way. If this had been linear, like we've dealt with in the past, we would be going up or down by a constant amount that we would just add or subtract. All right, let's look at a couple of problems. Some of these it asks us to graph. but I'm just going to talk about them just a little bit so we can just see what are we looking at. If I was going to graph y equals 2 to the x, what I actually want you, well, let's do this. What is the y-intercept and what is the domain and range? Let's talk about that. These are good words that we need to get used to anyway. Okay, so if I want to graph this, I could make a little table of values. I don't actually need a whole lot going on here, but let's try something negative, like maybe -2, and maybe we'll try 0, and maybe we'll try 2. Let's try that. So 2 to the -2 is going to be 1 over 2 squared, or 1/4, so that's a fraction. 2 to the 0 is always 1. Anything to the 0 power is 1. 2 squared is 4. So I notice that as I get bigger, this is growing. And it is growing by a factor of 2. The growth factor is 2. The starting amount is going to be 1. The starting amount is on the y-intercept, the same as usual. It is right here. This is true. If we have a 1 for the a, when we have y equals a b to the x, in this case b is 2 and a is 1, because it's not, it doesn't show up, so it will always be a 1. If we graph this, we're going to notice that, let's see, 1, 2, and 1, 2, 3, 4. Here's a point. And then this one is a fraction. So this is one of these that looks just like this, exponential growth. That's going to get smaller and smaller. That's going to get bigger and bigger to the right. So the y-intercept is 1. The domain is, what can x be? Domain is a question about x. Well, when we are looking at domain, we look left to right to say what can x be. Well, as we go this way, x can be, it can get smaller and smaller and smaller forever, right? And as we go this way, it can get bigger and bigger and bigger forever. So x is going to be all real numbers. Domain is going to be all real numbers. Sorry. All real numbers. Because it goes way negative and way positive. And then we switch, and let's talk about range. So range is, what can y be? So we switch and we look up and down and we say, are there any limits on what y can be in this graph? Well, yeah. Notice that y never goes below this point. It can go up forever, right? It can go up forever as this line goes up forever. But this kind of bottoms out and never ever gets down to 0. And so what we're going to do is we're going to say y has to be greater than or equal to 0. Okay. X was all real numbers. For the domain, talks about x. Range talks about y. Y has to be greater than 0, because this line right here never drops below. There's nothing down here. And so y has to be greater than or equal to 0. All right, so that's a good example of that one. Let's chat about one that has a fraction in it and maybe a different starting amount. Y equals 3 times 1/4 to the x. Okay, so if I want to know about this graph, I might want to make a table of values. Let's just kind of do a similar thing here. Let's say we had a -2 and a 0 and a 2. We'll know pretty soon if those were wise numbers to choose. we have 3 times 1/4 to the negative 2. So that negative fraction or negative exponent wants me to flip over the fraction, 4/1, keep the exponent, but it's not negative anymore. 4 squared is 16, and 16 times 3 is 48. So this is going to be 48, pretty big. And then 0, I'm going to have 3 times 1/4 to the 0. 1/4 to the 0 is 1 or 3. So the y-intercept is still the starting amount, just like is still the starting amount, just like it was with linear equations. Let's see. So that's going to answer the question about y-intercept. That's the y-intercept. And then let's see, 3 times 1/4 squared. So, that's a lot of fraction going on because it's 3 times 1/16, because we square the top, square the bottom. 3 times 1/16 is some really small fraction. That is, I don't know what I was thinking. That's not so hard at all. It's 3/16, because it's 3/1 times 1/16. Anyway, that's still a pretty small fraction. What we're going to see is we have a graph that looks something like this. Here's x, here's y. We can't even really graph this. At -2, it's coming down from way up there. 0 and 1, 2, 3, and then 2 and barely above the line. So here's what this looks like. It's coming down, it's coming down, it's coming down, and it just keeps getting smaller like that. That's not a very neat graph, but that's exponential decay for you. So what I want to ask is, what is the domain? Let's switch colors here. Domain. Domain is asking, what can x be? So I want you to think this direction. X, what can x be? Well, x can get bigger and bigger and bigger this way, and smaller and smaller and smaller this way. So it can be anything. All real numbers. And then what can y be? Let's talk about domain, range. Range and domain are the same thing. One just talks about x, one talks about y. So range looks like this. So we switched to talking about range up and down, and notice that y can go up forever, but as it comes down, it never gets lower than this amount. So again, we're going to say that the range y has to be greater than or equal to 0. So this is pretty typical, these two answers of exponential functions. You're going to do some practicing in Alex, and let me know if you get stuck on anything. I'd be happy to help. Let's go back and review just one thing here. This is the key concept that I need you to make sure that you wrote down and defined really well. Exponential functions come in this form: y equals ab to the x. X is the exponent, and a is the starting amount, b is the growth factor. How is it growing? Is it growing a lot? The bigger this growth factor gets, the bigger the number is, the faster it's growing. Or is the growth factor actually a fraction? If the growth factor is a fraction, it is decaying. We're either growing or we're decaying. And if the growth factor were a 1, then nothing would happen. It would stay exactly the same, because we would just never grow and never decay. So, all right, hopefully you took good notes. Make sure they're pretty clear, submit your notes on the lesson in Google Classroom.